Good morning, Professor. Today I'm going to present about harnessing machine learning more methods for accurate agriculture crop yield prediction. Agriculture industry is the backbone of the global food security, which sustains the billions of people across the globe. It is facing many challenges right now, such as climate change and population growth, which is increasing the demand for the food, and the industry is currently is not able to fulfill that demand. So there is a need for making the optimization in the crop yield. The data-driven approaches help us uncover the patterns of the complex data sets, complex data sets, and with the millions of records. Modern agriculture industry and agribusinesses increasingly leverages the data for precision farming. The objective of this data science pipeline is to develop a supervised machine learning model to predict the crop yield based on the different environmental factors, different environmental factors and soil types and management data. The agriculture productivity has main two challenges: environmental variability and soil variability, which can hinder the consistent yield. And secondly, the limited use of the data in the decision-making processes. The goal of this project is to identify the critical factors influencing the crop yield and build a predictive model to guide the farmers and policymakers in optimizing productivity. We have collected the data from the Kaggle, which contains around a million record with the features region, soil type, and crop, which is the categorical features, as well as there are numerical features such as rainfall, temperature, days to harvest, and some of the management data as well, such as fertilizer used and irrigation. In the figure that is present in the right side, we can see the different features with respect to their data type. Now let's move on to the exploratory data analysis part, where we first analyze the distribution of different quantitative features. The rainfall and temperature distribution shows the uniform across their respective ranges, suggests that data coverage for various environmental conditions. Fertilizer and irrigation values show us a bimodal pattern, which indicates the distinct farming practices. Crop yield, which is our dependent variable, follows a normal distribution, mostly centered around the 4 to 6 tons per hectare, which suggests that the most crop achieve the moderate productivity with minimal outliers. The chart of the count of crops with respect to uh, weather condition can show us many underlying patterns, such as all the weather conditions support diverse crop cultivation, while the rainy conditions shows the highest crop count, aligning with the water demands of the crops like rice and soybeans. Crops such as rice and soybeans are more prominent in the rainy conditions, while cotton and barley are evenly distributed across different weather types. Climate adaptation strategies are crucial for optimizing crop yield under changing weather patterns. Different crops, count of the crops by soil type can show us the other patterns, like each soil type supports diverse crops with a relatively balanced count across all the soil categories. Crops like rice, soybean, and wheat appear predominant compared to others. The stack bar chart shows all the types have comparable distribution of the crop types, suggesting soil diversity the diversity is equal potential. Clay and loam soils are likely favorable for diverse crop growth, while a crop-specific analysis is necessary for optimizing farming. After completing the EDA, we'll move on to the data processing pre-processing part, where we first find out the missing values present in the data set and impute it with the different strategies like mean, median, and mode. Then we'll use the one-hot encoding strategy for encoding the categorical data like soil type, weather condition, and region. And after that, we'll use this scaling for min-max scaling or standard scaling for the continuous features like rainfall and temperature. Then, once the pre-processing is done, we'll move on to the feature engineering section, where we'll create two new features. One is the rainfall temperature product, and other one is the irrigation and fertilizer product. The first new feature, rainfall temperature ratio, can help us identify the rainfall and temperature combined effect of the rainfall and the temperature, and also allow us to show the binary indicators for extreme weather conditions like drought and flooding. Then in the feature selection section, we have utilized the correlation analysis to remove the redundant features that we can conclude from the correlation matrix shown in the figure available in the right side. This is the new data points that we have created. Then we'll move on to the model building section where we have built the two supervised learning model and one unsupervised learning model. The supervised learning models contains the ridge regression and decision tree regressor, while the unsupervised learning model called K-means. The ridge regression utilizes the L2 regularization to reduce the multicollinearity and overfitting. The regularization strength can be set to 1,000 for optimal performance. Ridge regression captures the most linear relationship effectively, but it struggles with the non-linearity. So, to avoid that, we have utilized the decision tree regressor, which captures the non-linear relationship and feature interactions most effectively. To control the overfitting in the decision tree regressor, we have used a few parameters, namely max depth, minimum sample split, and minimum sample leaf. We have utilized the absolute error, mean square error, and R2 score as the performance matrices to evaluate the supervised machine learning models. The supervised machine learning models, the decision tree showed us the R2 score of 91.16, and the ridge regression showed us the R2 score of 91.28. If you talk about the mean absolute error, then ridge regression shows us that it struggles with the nonlinear trends in the data, while decision tree reduced the mean absolute error by almost 37% compared to ridge regression, which is better alignment with the actual yields and captures the nonlinear dependencies as well. If we go to the code, then we can see the k-means. We have utilized the elbow method for the optimal clusters to find out. And if we can see in the chart that the elbow is created around 4. So the 4 is the optimal number of clusters for the k-means for our data set. Then we have utilized the Silhouette score method to evaluate the k-means as well, and it is around 99.75, which shows us the best clustering accuracy till now. Then at the last, we have utilized the randomized search CV for the hyperparameter tuning. We have tuned the decision tree regressor model with the hyperparameters like maximum depth, minimum sample splits, and minimum sample leads with the threefold cross validation to ensure that the model generalization across the different data subsets. Some of the key insights that we can get from this particular data science pipeline is that rainfall and temperature are the primary yield influencers, while fertilizer and irrigation management have a region-specific impact. Now, we can apply this particular data science pipeline into the tailored advising for irrigation scheduling and strategic planning for resource distribution in the regions with poor yield potential. There are some strategies we can deduce based on this particular pipeline for yield optimization. One is that implement a targeted irrigation plan in the regions with water deficits. Another strategy could be adjust the fertilizer types and quantities based on the soil types analysis, and then deploy the crop rotation technique in the regions with declining yields. So that's it about the data science pipeline. Let's move on to the main data science pipeline, where from the start. So this is the data science pipeline I have created. Initially, I have imported the required libraries such as pandas, numpy, matplotlib, and seaborn to visualize the data. Then I have loaded the data using the read CSV method. This is the data overview of the data. where there are categorical features like region, soil type, and crop. There are some continuous features like rainfall and temperature as well. That is the information of the data and its data type as well. Some statistics for the data using the data.describe method, which shows us that minimum rainfall is 100 and the minimum temperature it can go up to the 15 degrees Celsius, 15 degrees Celsius. Then we'll move on to the EDA part where we have plotted different charts to uncover the patterns or with the different soil types versus the crops, different regions versus crops. In this particular chart, we can see all the regions have almost equal amount of crop yields. After this section, we can move on to the correlation matrix to remove the redundant features. We can, in particular, in this particular heat map, we can see that fertilizer used and irrigation used, they are positively correlated, while the fertilizer used is highly correlated with the yields per ton, and rainfall is also positively correlated with the yields per ton. However, the however, the temperature is negatively correlated with the yields per ton. After that, we will move to the data pre-processing part of the pipeline. First, we will check for the missing values if there are any present in the data set. After that, we'll encode the categorical variables like region, soil types, and weather conditions using the one-hot encoding method. We utilize the standard scaler to scale the continuous variables like rainfall, temperature in Celsius, fertilizer used, and irrigation used. Then in the feature engineering section, we have created two new features like rainfall temperature ratio and the fertilizer irrigation product using these two formulas. This is the overview of the newly created features. This chart shows us the distribution of the newly created features, which shows that fertilizer irrigation product is a binary feature where most values lies between -1 to 1. After that, we'll move on to the model training section, where we have splitted the data into the training and testing part. The training part contains the 80% of the data, while the testing part has the 20% of the data. The regression model is trained with the 1,000 regression strength to have the optimal performance. It showed us the 91.28% of the R2 score and mean square error of 0.25, while the decision tree regressor shows the mean square error of the 0.25 and R2 score of 0.91. And then we have trained unsupervised machine learning model of k-means. We have used the elbow method to find out the optimal clusters. Here we can, from the chart, we can conclude that the number of clusters are optimal for our data set. We have trained the k-means model here, and then utilize the Silhouette score method to evaluate the performance of the k-means. It shows us the 99.75% of the score, which shows which can from which we can conclude that the cluster quality is very good. And if we compare the graphs of the mean absolute error, mean square error, and R2 score for the supervised machine learning models of decision tree and ridge regression, then it shows that decision tree shows us the higher R2 score, which makes it efficient model for this particular data. And if you plot the graph of the actual and predicted values for the decision tree regressor, then it can show us that almost all the values are predicted accurately by the model. For example, if you can see in this data set, the actual value is 3.44, while the predicted value is 3.49, which is negative 0.05 difference. And similarly for the other value as well, which is 5.25. and the predictor value is 5.16, which is around 0.09 difference. So this particular pipeline help us identify the different crops and utilizing the different environment types, soil type, and according to the weather conditions as well. And this can greatly help the policymakers and the farmers, also the agribusiness businessmen, to have the optimal crop yield, utilizing the resources at their best. Thank you.